right, hello and welcome to the problem-solving portion of this lesson. This goes along with the 1.1 notes that you have hopefully already watched. If you haven't watched those, make sure you watch that video first. I'm going to go through, I think, 4 example problems that are important for us to be able to know how to do. Okay, and actually the first assignment that you're going to have from me is going to have more than just these types of problems, but these should be 4 good problems to sort of get you started and get you on the right path. So let me show you what we're working with here. So I've got my full webcam view, I've got the slides, and then I also have a document camera where I'm going to actually be able to do some calculations, and you will be able to follow along with me, because this is kind of like a whiteboard, all right, of sorts. Okay, so without any further ado, let's go ahead and take a look at the example problems. So this is actually one of the problems that I'm going to have you do for the homework assignment, but it's just the first 2 parts, so A and B. I think there's like A through F or something, so you can skip the first 2, or you can include these in your homework assignment. It doesn't really matter to me, but okay, so let's go ahead and look at this. So we're going to be performing unit conversions, ounces to kilograms and liters to gallons. All right, so let me go ahead and write this down. So this was chapter 1, number 46, part A. The problem was 908 ounces to kilograms. All right, and we're converting this value to this value, but we just don't know how many this is, right? So think of like inches and feet, right? Convert 36 inches to feet. Well, that's 3 feet, right? Because it's 12 inches per foot. Same type of problem here, except I don't actually know what this conversion rate is. I don't know how many ounces are in a kilogram. I don't know how many kilograms are in an ounce. So that's why we have technology, right? So I'm going to go ahead and pull up my phone here. I've been doing some looking up of stuff myself here before I made the video, so go ahead and delete that. All right, so it is as simple as this. Type in this second part here, ounces to kilograms, and you're going to get something like this pops up on Google. All right, Google is pulling this information from somewhere, but it's got it here listed for us. So we're just going to go with this right here. Okay, so you see how it says 1 ounce is equal to 0.0283 kilograms. I'm going to go ahead and just write that down verbatim right here. And I'm going to abbreviate kg. Okay, so kilograms is abbreviated kg. All right, so that's the piece of information that I need. The way that you actually solve this problem mathematically is through the use of dimensional analysis, and that is something that I mentioned in the slides from last time. It's just a method for solving problems like unit conversion problems. So here's how this works. I'm going to rewrite my original number, or my original value, my starting value, and every time we're going to be multiplying by a conversion factor. Okay, this is our conversion factor. Okay, conversion factor. This tells us how these 2 units relate to each other. Okay, so this information is going to end up going here. All right, and we want our final answer to be in kilograms. Okay, so this is sort of the setup for the problem. The next step is to figure out what exactly goes here. We know it's going to be this conversion factor, but this is written like an equation, and this is like a fraction. So the way that this works is we're going to analyze the dimensions. Okay, dimensions and units sort of mean the same thing. We're going to analyze the units in our problem, and that's going to tell us what goes here. Okay, and where this information goes. So here's how this works. Over here, I have ounces, the unit ounces in the numerator. Okay, technically, you could write this number like this, 908 ounces over 1. Okay, so ounces is in the numerator. All right. Units are kind of treated like variables. Okay, so in math class, you may have seen something like this, x squared over x, right? Well, with variables, you can do this, right? If something is in the numerator and the denominator, then it cancels out, right? So x squared is the same as x times x, right? And so if I have x and x both in the numerator and the denominator, I can cancel them out, and so this is just equal to x, right? So it's the same thing with units, okay? If I have ounces in the numerator and I want it to go away, right, because my final answer is in kilograms, then I have to put ounces in the denominator of my conversion factor, okay? And if I want kilograms to show up, then I need to put kilograms in the numerator, right? Because I don't have kilograms over here, but I want it over here, so that needs to go in the numerator. So here's what happens, right? You have ounces in the numerator, ounces in the denominator, they cancel out, okay? And you're left with kilograms, which is the destination, okay? So these are just units though, right? There's no numbers here. So what goes here? These numbers go here, okay? So 1 ounce, that's on the bottom here, is equal to 0.0283 kilograms. The numerator and denominator of the conversion factor need to be equivalent. They are equivalent, okay? If they're not equivalent, then it's not a conversion factor, okay? So, there we go, all right? The problem has been set up. We are ready to go ahead and calculate, right? Because my ounces are canceled out. I'm going to be in kilograms, so now I just need to do the math, all right? So let me pull this back up. Let me go ahead and open my calculator. All right, so I'm going to do 908. Remember, anytime you divide by 1 or multiply by 1, you don't actually have to type that in, right? It's not going to impact the calculation. But I do have to multiply by the numerator here, 0.0283. Oops. It would help if I actually hit the multiply button. 0.0283. There we go. So just for now, I'm going to go ahead and write that entire number down, 25.6964 kilograms. One last thing I want to show you before we call this problem done. This is a lot of numbers here, okay? And my starting number, 908 ounces, this only has 3 significant figures, okay? This answer has like 6, okay? So we should try to match this up, okay? Now I want you guys to practice this. That's the goal. You know, it's okay if we're not perfect at this, right? But the goal is to, you know, work on it. So if our starting number is 3 significant figures, our final answer should be 3 significant figures. So what I'm going to do is I'm going to round this number to 3 significant figures. Okay, so 25.6, but the 9 causes the 6 to round up to a 7, so 25.7 kilograms is my final answer. And this is what I would like you guys to do. Okay, so whenever you get to a final answer, put it in a box or a circle. Okay, that way, you know, when I'm looking at your assignment, looking at your work, I'm like drawn towards the answer. Okay, it kind of helps clean things up a little bit. Okay, let's look at part B, the second problem here. This is 12.8 liters to gallons. Okay. Once again, just like I didn't know what the ounce to kilogram conversion factor was, I don't know what liters to gallons is. So I'm going to pull my phone back up here, and I'm going to search liters to gallon. L to gal is good enough. Google is smart. Okay, so 1 liter is equal to 0.264 US liquid gallons. Okay, so 1 liter is 0.264 gallons. All right, so that's the information I need. That is eventually going to go in this portion of the problem. If we're sort of using some pattern recognition here, right? I'm going to start with my original number, 12.8 liters, multiply it by a conversion factor, and my answer is going to be in gallons. Okay, let's practice that dimensional analysis again, right? Ounces was in the numerator, ounces therefore had to go in the denominator. Liters is in the numerator, therefore liters must go in the denominator. My destination was kilograms, so I had to put it in the numerator. My destination is gallons, so that must go in the numerator. Okay, then I can fill this in with these values from the conversion factor. 1 liter is equal to 0.264 gallons. Okay, that's it. All right, my liters are going to cancel, and I'm going to be left with gallons. Okay, pull up the calculator. 12.8 times 0.264 divided by 1, so I don't have to actually do that on the calculator. 3.3792. Once again, we have 3 significant figures in our starting number, so I'm going to round to 3 significant figures here, 3.38, because once again the 9 causes that to round up. Okay, so that is my final answer. Okay, so you've got a few more problems to do that look like that, along with some other various exercises. I am going to tear this page off, and we are going to start with the next set of problems here. Okay, so let me pull this back up on the slides. Okay, so now we're going to do this a little bit more complicated. We're still going to be doing the same sort of thing. We're still going to be employing dimensional analysis to solve these problems, but now instead of just doing like ounces to kilograms or liters to gallons, we're going to actually be talking about those 3 ways of measuring substances. So if I back things up a little bit, we talked about moles in the previous video. You can measure the mass of something, you can count the number of individual particles, or you can count the number of sets. Okay, so you can measure mass, number of particles, or sets of particles. And remember, this was moles. Okay, we're going to be converting between these 3 different things. Okay, and actually, if I back this all the way up to the learning objective for this topic, it says here, calculate quantities of a substance or its relative number of particles using dimensional analysis in the mole concept. Okay, so this is exactly what this entire lesson is all about. Okay, so let's go take a look at the problem. Got 2 of them here. All right, let's just start it off. So go to the document camera. First one, calculate the number of atoms in 25.0 grams of aluminum. Okay, I'll write that out so you can see it here. Calculate the number of atoms in 25.0 grams of aluminum. And, you know, I'm a chemistry teacher, right? So I recognize that aluminum is an element on the periodic table. So I'm going to go ahead and use its abbreviation, Al. Here it is on the periodic table, capital A, lowercase l. That number there is going to become important to us a little bit later. So yeah, I'm used to abbreviating things. So that's A, capital A, lowercase l for aluminum. Okay, so here's our prompt. Calculate the number of atoms in 25 grams of aluminum. Well, how do we do that? So let's go take another look at the slides again. Okay, let's go back to where we were in the video. Okay, so we talked about this concept of molar mass. Okay, and I want to focus you down here at the very bottom. It says here, molar masses are in units of grams per mole. And remember, moles are sets, right? So, a mole is 6.022 times 10 to the 23rd of whatever it is you're talking about, right? Like 1 dozen is 12, 1 mole is this massive number. This molar mass is the first thing that we need to use, okay? Not of carbon, but of aluminum, okay? And let me show you why, okay? If we can figure out how many moles of aluminum this is, then we can use that number of moles to figure out how many atoms that is, right? Because 1 mole is 6.022 times 10 to the 23rd atoms. So we're going to use these grams to figure out how many moles of aluminum we have. And then we're going to do a second step where we take those number of moles and multiply it by that number, 6.022 times 10 to the 23rd. It's kind of like if I said that I had like 50 pounds of donuts, but you knew that 1 pound of donuts was 1 dozen donuts, right? So if you have 50 pounds of donuts, that means you have 50 dozen donuts. And then to figure out how many donuts you had, you would just multiply by 12, right? It's quite literally the exact same thing, okay? Just with grams, moles, and number of particles instead of pounds, dozens of donuts, and individual donuts. Okay, it literally is the exact same thing. So let's set this problem up. Okay, I am just like on the previous problems. I'm going to start with my original number here, grams of aluminum, 25.0. Like I said, we're going to use the molar mass of aluminum to figure out how many moles of aluminum there is. Okay, so let me actually pull out the periodic table here. Okay, so here we got aluminum at the bottom of your screen. That number right there, 26.98, that is the molar mass for aluminum. Okay, that means that 1 mole of aluminum weighs 26.98 grams. Okay, so let me actually write that down. 1 mole of aluminum is equal to 26.98 grams of aluminum. This is our conversion factor. Okay, so just like we had to look up like how many ounces is in a kilogram, the periodic table gives us these conversion factors. Okay, 1 mole of aluminum weighs this much. So here we go. I've got 25.0 grams of aluminum. I'm going to use this conversion factor along with my understanding of dimensional analysis. I've got grams of aluminum here. So to cancel that out, I'm going to put that in the bottom. My destination is going to moles. Yeah, I shouldn't have that E there. The abbreviation for mole is to take the E off. We're saving a lot of time with that, right? Okay, so there we go. Got my conversion factor set up. I just need to put in these numbers. Okay, 1 mole on top is the same as 26.98 grams of aluminum. And so that calculation there is going to tell me how many moles of aluminum I have. Okay, the grams are going to cancel. There we go. So let's get the calculator out. All right, so 25.0 times 1, so I'm going to skip that part, and then divided by 26.98. Okay. All right, so 0.9266, I've got 3 sig figs here, so I'm going to do 0.927. Okay, 0.927. And that is moles of aluminum. Always, 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 guys, include your units. Don't ever leave like naked numbers around, okay? Because then things start getting really confusing, right? If you're already feeling a little bit overwhelmed or confused, not putting units on numbers makes it even worse, okay? And in fact, when I'm grading stuff, if numbers don't have units, then I'm going to need you to fix that, okay? And on the AP exam, for example, if numbers don't have units, then you don't get points, okay? So, all right, we have 0.927 moles of aluminum. Remember, the question is calculate the number of atoms. Well, we had this number. It was 6.022 times 10 to the 23rd. I never told you what that number is called, by the way. This is called Avogadro's number. Okay, and this number is in units of particles per mole, or particles per 1 mole. Okay, so there are this many particles per 1 mole. So really, you could write this as one big fraction like that. 6.022 times 10 to the 23rd particles per 1 mole. So, you might see where I'm going here. I'm going to take this number and multiply it. Okay, this is another conversion factor. Okay, so just how the molar mass was a conversion factor, so is this. I'm going to basically just multiply by this thing right here, because I've got moles of aluminum. So I'm going to put moles of aluminum down here. I want to know number of atoms, so atoms of aluminum. And those units match up with these, right? Particles and atoms mean the same thing. So I've got on the numerator here 6.022 times 10 to the 23rd atoms of aluminum is the same as 1 mole of aluminum. Okay, that's what Avogadro's number tells me. So that's my final part of the calculation. That's like my second step. I'm going to cancel out moles of aluminum, and I'm going to be left with atoms of aluminum, which is what I want to know. So let me get the calculator back out here one last time and proceed with the calculation here. 0.927 times 6.022 times 10 to the 23rd. Okay, let's tackle this really quickly here. So you may not be used to seeing numbers like this. Maybe you are. First of all, we've got 3 significant figures here, right? So I'm going to do 5.58. So all this other stuff I'm not going to care about. But this I do. Okay, so this E, this is calculator language. E23. What this means is this. 5.58 times 10 to the 23rd. Okay, so E means times 10 to the that number. Okay, E stands for exponential. Okay, and this is atoms of aluminum. Okay, once again, I'm gonna box my very final answer. Okay, all right. Let's look at one more example of this. Tell you what, I'll just draw a line here, and we'll scoot the page up. Let me go back and actually show you the slide here. So, final problem for this video, calculate the mass of 1.25 times 10 to the 24th molecules of ammonia. Okay, so let's and here we have a picture of what ammonia looks like. It's 1 nitrogen with 3 hydrogen atoms sort of connected to it there, or bonded to it. Okay, that's going to be important a little bit further down the line. This first problem was only talking about the element aluminum, so we were able to just look up its molar mass on the periodic table. Well, now we have a combination of elements, and so we're going to have to use the periodic table plus a little bit of adding to figure out the molar mass for ammonia. But we're not there yet. So let's just head back to the document camera here, and let's write down the problem. Calculate the mass of 1.25 times 10 to the 24th molecules of ammonia. And like you saw in the image from before, ammonia is NH3, 1 nitrogen, 3 hydrogens. So that is what I'm going to use in this problem here. I'm not going to write out ammonia every single time. Okay, so we've got a bunch of molecules, 1.25 times 10 to the 24th of them, and we need to figure out how much that weighs. Okay, this is the exact opposite of this problem from before, right? Here we were starting with number of particles we were starting with mass and we were going to number of particles. Here we're going to start with number of particles and we need to figure out the mass, okay? So we're basically just going to do those two steps that we did up there, but in reverse, okay? So let me show you how that works. 1.25 times 10 to the 24th molecules of NH3. That's my starting number. I need to figure out how many moles that is. Okay, so think of this as like, okay, I've got like 1,000,000 donuts. How many dozen donuts is that, right? So in that situation, you would just divide by 12, right? Well, in this situation, since we're talking about atoms and particles and molecules, we're going to divide by Avogadro's number. We're not going to divide by 12, but we're going to divide by this big number, okay? And that actually does make sense when you look at the units, okay? If I have my molecules of NH3 in the numerator here, that needs to go here in the denominator, and I want to figure out how many moles I have, so that's going to go here in the numerator. So molecules per mole is like particles per mole, right? And remember, the actual big number here goes with the particles unit. Okay, so it's going to go in the denominator. It's going to be dividing by Avogadro's number, 6.022 times 10 to the 23rd molecules of ammonia per 1 mole. Molecules of NH3 cancels. I'm going to be left with moles of ammonia. Okay? I'll go ahead and figure out what that equals. Okay, so I've got 1.25 times 10 to the 24. Okay, I want to talk about something really briefly here that is very important. Anytime you divide by Avogadro's number, okay, so anytime this number shows up in the denominator, please, please, please put it in parentheses, okay? If you don't, you are going to encounter some issues, okay? If you're using a fancy calculator, like a TI 83 or 84 or 89 like I have here, and you use the little fraction dividing thing, then you're probably going to be okay. But if you're using any other type of calculator or the calculator on your phone, whenever you divide by Avogadro's number, put it in parentheses, okay? It's because of this exponential part here that you might encounter some issues if you don't. So divide by 6.022 times 10 to the 23rd. And look at that, I actually get a relatively reasonable number. I have 3 significant figures over here in the beginning, 1.25. So 2.08 is going to be my temporary answer here, 2.08 moles of NH3. Now I need to figure out the mass, right? So I know how many dozens I have or how many moles I have. How much does that weigh? Well, if we look back at the previous problem, I need something like this, right? 1 mole of aluminum was 26.98 grams. I want to know how much 1 mole of ammonia weighs, okay? So 1 mole of NH3 is equal to question mark, question mark, question mark, grams of NH3. What's the answer? Well, you could just Google it, okay? But if you're on the AP exam, or for example taking a test or a quiz from me, well, you're not going to have Google on the test, right? So it's pretty simple. You just look at your periodic table, okay? Instead of looking for aluminum, like we did in the last problem, we're looking for nitrogen and hydrogen, okay? Ammonia is 1 nitrogen and 3 hydrogens, okay? So take a look at your periodic table. Nitrogen has a mass, or a molar mass of 14.01. This is grams per mole. And hydrogen has a molar mass of 1.008 grams per mole. Okay, so for ammonia, it is 3 hydrogens and 1 nitrogen, right? So times 1 times 3, this is still 14.01. This is, oh boy, 3.024. I think that's the right answer. You guys can fact check me. I hope I'm doing that right. You know what? Just to be safe, let's just make sure. Okay. So don't want to be wrong on my first video here, do I? All right. So this times 3. Okay, I was right. And so then what we're going to do is we're just going to add those together. Okay, for the overall molar mass of ammonia. So this plus 14.01. Okay. So I've got 17.034. Once again, if we want to be super nitpicky about the significant figures, this number starts with 4. This number starts with 4. Magically, we have a number that has 5 sig figs in it. So I'm actually going to chop off that 4. I'm going to round to 4 decimal places. There we go, 17.03 grams per mole. That means 1 mole of ammonia weighs 17.03 grams. Okay, so that is going to be the important part for the final part of the calculation. Okay, so at the bottom of my page here, I'm going to take this answer that we had from before, 2.08 moles of ammonia, and I'm going to pay attention to my units, right? Moles has to go in the bottom. Grams, right? Calculate the mass, that's what we're going towards. Has to go on the top. I have those units here. That's the whole point. That's why we did this. And I'm going to plug in those numbers here, right? So 1 mole in the bottom and 17.03 grams on the top. Okay, so last bit of calculation here, 2.08 times 17.03 is 3 sig figs in our starting number. Really, it's this starting number that we should be paying attention to. 3 sig figs here, so 3 sig figs on this answer would be 35.4. And our moles cancel here, right? So grams of ammonia. Okay? All right. Now, guys, I'm writing a lot of work here, okay? If you want to do like this whole thing, like just, in your calculator and not write it down, that's probably okay, right? Do you need to write this down every single time? Do you need to write Avogadro's number down like this separate every single time? The answer is no, okay? Maybe the first time you do it, you might want to write it down, but we're going to get good at this, and so really this part here is what I need to see, right? This part here, the actual calculation, okay? I do want to see these calculations written out like this, with the units, shown how they're canceled, displaying, exhibiting that you know how to do the dimensional analysis. Okay? All right. So that was a lot. I did promise this video would be shorter, and look at that, 34 minutes. That's 1 minute shorter, so I wasn't lying. Okay. All right, so hopefully you get a chance to watch this, hopefully before class, but if you don't, we're going to do some more examples like during the Zoom meeting, and then you can maybe refer to this as a supplementary resource. The goal is to just learn it, right, and to know how to do it. So I will see you guys in class, and hope you have a nice day.